Good morning, guys. I'm here. Let me just finish this little thing here. I want to test a thing before we start, but it seems like there's more people than last time. That's great. So, can you hear me? Type something into the commands, please. And the target surface, here we go. Okay. Yeah, works. Perfect. Okay, hi everybody. Today we're gonna be touching on a huge topic called local coordinates, or T and UV coordinates, or something like that. Um, that's a very useful thing, and again, it's a general approach, so it kind of makes sense to understand it and then really try to explore it on your own. So I'm gonna show you some useful things and useful special cases where things can be confusing and so on. But we're gonna be mostly focusing on all the components which have evaluate in their name. So it's gonna be evaluate curve first, then evaluate surface, even evaluate box. There's evaluate mesh. Even evaluate fields, but there are other things which are related to UV coordinates. So this is the topic for today. And after we finish here on YouTube, I would like you to really help me test the other ways of sharing, because in here in on YouTube, when I double click, you don't see what I'm typing into the search box, and you just see the component appearing. And I believe this is one drawback, and the other one is I cannot hear you. So typing a command is really not making the conversation fluent. So after we finish here, on the website there's a link, and if you're using Microsoft Teams, I would be really glad if you join me just for a few minutes. It's gonna be an extra lesson with some hidden stuff. Maybe help with the exercises or something like that. So we're gonna be testing that after this is finished. Okay, I can see 10 people connected. That's not enough, but well, 12. That's better. Okay, so let's jump into it, and let's hope we can. We can meet in bigger numbers, maybe on the Teams, because there's direct feedback. Okay, so I'm gonna hide this thing because that's for later. I'm just gonna. Okay, here we go. I'm gonna jump into a new file for this, so that you don't have anything confusing here. But we're gonna be focusing on the evaluate components. So here we go, new file. Let's start with evaluate curve. So that's this one. We need bifocals for this. Here we go, that's the name. And like maybe how many of you already use this regularly and are totally okay with this? Just type into the commands like, I know it's my favorite. Just say something if you really use this guy. If not, you can type something as well. I just want to know how many of you really will benefit from this lesson here. Yeah, this is what I'm talking about. It takes a lot of time. Okay, great. Okay. You know it. Perfect. Okay, that's good. So this one is pretty awesome. So let's first jump into Rhino and let's create a curve in Rhino. So I'm just gonna zoom in a little bit. So I'm gonna make a little curve here, just using the curve command. It's not gonna be twisting, like it's gonna be there and back again, something like this. Okay, so this is my curve. I'm selecting Rhino and I'm referencing it back, sorry, into Grasshopper. So curve component for that, right click, set one curve. Okay, so now we have this curve back in Grasshopper, and this component is doing something you should remember from high school mathematics, because any kind of curve has a t parameter on it. If you just open a browser window and you just type parameter t or parametric curve equation, you're gonna see a letter t somewhere in there, and that's how it works. So any kind of curve has a t parameter on it, and that means t is a number, so we can put in a slider. So I'm gonna make a slider of 1.2 or something like that. When I connect this parameter t into that curve, you can see that I'm having a point on that curve. And as I slide with this slider, sorry, the point travels along the curve. Well, you know, that could be useful, maybe for camera positioning in some animations, or I don't know, whatever. But the problem is, when we are at 0, it should be at the beginning of the script. But when I reach number 10, I just get just over here and not to the end of the curve. And the problem is that we might not know where's the end, like what kind of number should the t be so that we get to the end of the curve. And this thing can be actually remedied by using something called reparameterization, because the t parameter is related to curvature, length of the curve, degree of that curve. So if I change that curve, my position on that curve changes as well. See that? When I change the curve, my position is like, now I'm here, and when I change the curve, I'm pretty further, away. Maybe the ratio is the same, but it changes. So in order to have some control over this, there is on this input over here, there is when you right click, there's an option to reparameterize. This is very important. I think we touched on that a few times already, but let's understand it today. So there should be this bell curve, like to make it maybe average, remember, from statistics. So if I have number coming from 0 to 1, so I create a slider with 1 on it, that means it's going to go from 0 to 1. When I connect this, and the curve is reparameterized like this, that means 1 is at the end and 0 is at the start of that curve. So now, providing numbers from 0 to 1, I have control over the whole curve, and I always know that when I provide number 1 exactly, I'll be at the end of the curve. So this is called evaluate curve, and it's I'm using it all the time. Like there's endpoints component, right? When you have a curve and you want to ask for the start point and end point, kind of useful. There's midpoint as well, curve middle, so you can put it in. But if you provide 0.5 over here, it's exactly the same point, right? Well, in this case, it seems that there's a little bit of gap, so maybe this one is calculating the middle in some different way. It's curved, so there are many ways. But just providing number and evaluate curve is usually the most universal approach. So I got used to this guy. There's a question. Oh yeah, If your slider goes from 0 to 1, that means you provided just one number, and well, if you don't have any decimal points, that means when you double click and hit R, so amount of decimal digits, and then you're gonna slide with the slider. Yeah, this is what happens all the time, and this is maybe the case why I don't like the fact that you don't see when I double click, you don't see what exactly I type in there. So we're gonna touch on that later. So is this evaluate curve, is it clear? That's a big thing, because once more, if I forget to reparameterize the curve, this disappears. You can slide with the slider, but the point is just on the beginning on that curve. See? And if your curve is maybe a result of some kind of, I don't know, intersection or something crazy, this parameter t can even not start at 0. It can go from -300 to 7,000 millions. You don't know. Of course, you can use a component called domain, and you can ask for the domain of that curve and put it into a panel. So we're gonna see what is the domain of that curve, and then we could actually make that slider work with this kind of domain. But when I change the curve, when I drag a point, this domain might change. In this case it didn't, but if I now it's a planar curve, see, it's flat. But if I go into space, the parameters might change. Oh, it doesn't. Oh well, I'm happy. But again, if this curve is something which comes from some crazy intersection, or it's created in some obscure way, you know, this number can change, and you don't want to check that all the time, because you're gonna say it's not working. So make sure that you always reparameterize the curve. I'm not gonna do it here. I'm gonna do it basically here on that curve, and you're gonna see that the domain becomes from 0 to 1. So now I'm totally sure that this slider is gonna work. Okay, so I believe it's time to move on. So why is this useful? Well, you know, let's take this curve again. I'm gonna just disable this part, and I'm gonna keep it reparameterized. And what I'm gonna do is I want to divide that curve. So I use this divide curve, we all know it. You know, now we have some equally spaced points on it, almost equally spaced, right? You know, this is useful when you want to, I don't know, then this might be a pathway with some trees on it, or it might be a chandelier, you know, hanging from the ceiling. So be creative with this, it can be anything. If you hit Control Alt and left click, you're gonna see from where this component originates. So it goes to the curve tab, and there's division. So there's all sorts of divisions, like maybe dash pattern or divide curve. That's the one we're using, divide distance. It's very computation heavy, but you know that the points are going to be equally spaced. Divide length, if you just need to be need the points to have the length on that curve in between them, like I don't know, like 1 meter. So you provide this one. There's even shutter. I've never used this one, but there's perpendicular frames, pretty useful one. And I'm talking about all these because, well, they are all basically using this evaluate curve component, but it's hidden somewhere in here. And sometimes it's so much useful to use the evaluate curve instead. So let's try to simulate this. Now we have some points on there. And in here we have the n inputs, so we can say we want 12 points on that curve. And, you know, this is the 12 points. And, well, kind of works nicely. And the output from here, that's cool to check. The output is points, and then tangents, like vectors going in the direction of that curve in that moment, in that point, and also the t parameter. So if you look at this output, you should see something which should be familiar already. So if I lower this number, you can see that we have numbers going from 0 to 1. And they seem to be almost equally spaced, but you know, there's this funny thing, a slight difference between this one and the evaluate curve. So check it out. If we use evaluate curve again on our curve, and we want to have 11 things so that we have the same amount of data, well, if we want to have 11 divisions, 11 points, the thing is we need a range, right? So I'm gonna have a range. I'm gonna say that the number of divisions in here should be 11, and you know, this should generate almost the same thing. See, maybe number 10 or number 9 is gonna be so much better, because then we're gonna have the same amount, like it's gonna be 10 units. And you can see the difference in here. So the green one is coming from the range, and the yellow one is coming from the divide curve. And you can see some difference, like it's slightly slower in the beginning, like over here is 0.1, over here is 0.03, so you know, it goes slower over here, but it finishes at 1 again. So when I use this, these points are somewhere else a little bit. So let me put spheres and boxes on each one. So mesh sphere, I'm gonna put mesh spheres on here, lower the radius maybe to 2 or something like that. And I'm gonna put boxes, center boxes with the size of 2 as well, in all 3 directions on these points. So now we can see that using evaluate curve takes the curvature in account. See there, in the beginning here, there's the curve is almost straight, like almost, it's curved but not much, and that's why these points go faster. See that? And over here it gets curved a lot, and that's why they are almost evenly spaced. But if you look at the spheres, they are trying to be as equal as possible. So sometimes you need this, and sometimes it's smart to take into account the curvature of that curve you're working with. So this difference is really important to us, and sometimes it's really you really need divide curve or maybe divide length. I'm gonna make a test here. Divide length. In here it's not about t parameter, it's about like length, so we can provide like 20 millimeters, and that's gonna make a different division as well. So 20 millimeters. I'm just gonna hide this for a moment. Yeah, maybe these as well. So you know, this division means that there's 20 millimeters of curve in between these 2 points. And again, over here the curve is curved, or it's bent, so it's not straight distance from this point to this one, but you know, if you traveled on that curve, you would have traveled 20 millimeters. And you know, this can be pretty tricky when you provide smaller numbers, right? You can have millions of points, because if you go below 0, this can be really small, so make sure that you don't screw this up. But like if I provide 0, it's screaming at me, right? Division by 0. But if I do 0.8, it's already a lot of points. So maybe if you have 1000 curves and you want to divide length, maybe this can get really slow. There's divide distance. That's even hard to work with. So I'm just gonna connect it. Maybe at 0.8 it's gonna be, yeah, see, this took like 1.5 seconds, because if you look at the icon, you can see that it's actually, it has to create a circle and then make an intersection with that circle, and that's your new point. And then again, from this point you make a circle, intersect it with the curve, and that's your point. There's a lot of logics and a lot of computation behind this guy, so you can see the difference. This guy is still pretty lightweight, but this one takes 1.5 seconds. So this is all about division curve. Maybe it's not all, but that's all the useful stuff. And believe me, evaluate curve, this one is the fastest one. So if you don't care exactly about the positioning and you want to take into account curvature, this is the best thing to do. Okay, so we divided some curves. That's cool. But what about, like in this case, let me just copy the curve, range, the slider, and evaluate. We're gonna make another version of this. Enable. Let's see the points. So in this case, it looks like it's already uneven distribution. So maybe you want something to like be you use some kind of crescendo or something to grow like as you come near, or something like that. Some kind of architectural gesture or something. Sometimes you let's put this on a straight curve so that we can see it clearly. So just gonna create a straight curve here, reference L1. And if we are on a straight curve, see, it works totally okay, nothing is irregular. But sometimes you want it to be irregular. So, you know, these numbers, if I again put a panel here, these numbers are, you know, equally spaced from each other, and if the curve is straight, we have this output. So if we want to make some more interesting, you know, something more interesting with the points here, we need to use Graph Mapper, our good friend. I hope it's your good friend. If not, try to you know, use it more. And we can provide any curve which starts at 0 and finishes at 1. So maybe of the graph types, maybe like this one is not useful, right? That's, well, we can try that, but you're gonna see that we don't have points everywhere, and if I provide more, you know, kind of not the thing, right? So let's try to select the graph type. I always use the Bezier curve because that's the best one for this example. So in this case, it's just 45 degrees diagonal, and that means, you know, it's one-to-one mapping. Let's give it a little bit less points. Okay, like this. And now we have these handles here, and I can say that in the beginning the points should be either like you know, closer to each other when I do it like this, or they can be further apart. And this can be very, very useful. This could be start of your script, right? You can say that I want things to be gradually growing towards this point. So we can go to some extreme like this. You can see that the other handle is going to be useful as well. So if you want something to be really, really like really aggressively accumulated at the end here, you have to use the other handle. Otherwise, I suggest keeping everything at the 45 degrees and try to play with one of them. So this is something you should become familiar with, because you've seen these things around in nature, you've seen these things you know, in physics and everywhere, and it's good to be able to you know, simulate something like that. So Graph Mapper is particularly useful in this case. And evaluate curve, you know, that's you cannot do this with all those components we've seen. So if you want uneven division, this is the way to go. So evaluate curve, Graph Mapper, and some number of points. Use like, you know, range divides the numbers. Okay, sorry for that. Is this clear? Can we continue? Any questions maybe to the graph mapper and this uneven division? Like we can set it like this extreme setting, and we can try to have the other curve and see what happens. How it's gonna look. Perfect. So set one curve, here we go, and this curve goes here. Yeah, and now we have the same thing over here, and I can try to reverse this, going like this, and I can go to a little bit more extremist. Yeah, it works even on a bent curve, so don't worry. You know, this is cool stuff. Okay, so evaluate curve. Let's move on to the next one. I believe that should be evaluate surface. And there's one little nice thing I want to show you about curves and surfaces. So in this case, we're gonna take let's build another curve in Rhino. I'm just gonna disable this. I'm gonna create a curve here, and I have this curve in Rhino here. It's going up and down, so I'm using control click to move it up and down, and then control click up. So this curve, it's a 3D curve, you know, something like this. I'm gonna reference it here. I have this curve, perfect. And let's make another curve, maybe in another direction. So first I'm gonna copy this, and you know, the easiest way to do it, if you have your gumball on, you just make a copy with hitting Alt, and then rotate it. Like, we don't have to, but it might be something like 90 degrees. I can change the points of that curve, so selecting that curve, picking one, moving it up. I'm gonna move this other one down a little bit. Yeah, curve like this, and I'm just gonna move it away from the grid because I don't want to, like, over here, so select it. Here we go. So I have the two curves here, and we're gonna learn that surfaces are actually, you know, just curves in two directions with this funny example. So, you know, there's this command called sum surface, and that's actually doing all for us. So, you know, based on the fact which curve is the first one, we can get a surface. Oh yeah, this curve is not referenced, so I'm gonna reference this curve. Yeah, here we go. This looks better. So first curve is here, second curve is here, and if I use the sum surface, it just takes the second curve and sweeps it along the first curve. So if I take this curve and move it somewhere else, nothing changes, right? But if I rotate it, it changes already. Yeah. So I think this is pretty understandable what's happening, right? And I just want to just for the sake of you know, understanding what surfaces are, I want to show you how to build this without this component, if this was not existing in there. So let's keep this as a reference. Maybe I'm just gonna make a copy of all and delete this surface here, and let's use the evaluate curve to do that, or, you know, let's understand that. So this is my first curve, and I can use evaluate curve to have some points on it. This time I can have just regular divisions. And what am I missing? Why it's just here on the beginning, just a few points in there? What's the problem? Why it's not doing points along the whole curve? Any ideas? No ideas? Try to type it in the commands. Reparameterize, perfect. I just want you to remember this, because this makes like half of my consultations really repetitive. Okay, so good. So we reparameterize, we have some curves, we can ask for more points, maybe 12 at least, you know, this goes all the way to 100, perfect. So we have the first curve, it's divided. And let's take the second curve and just try to position it from here to all the points over here. Like, how would you approach that? I have some points and I have this curve and I want to move it there. So, well, I just said it, move, right? So when I want to move things, I need move components. So what am I going to be moving? This curve. Perfect. And then I need some vectors, right? Because this input, the t from move, is actually asking for a vector. So I need to create a vector, right? So let's create vector out of 2 points. We need starting point of this one. So I'm just going to be consistent here. I'm going to say evaluate and I'm going to say 0. Well, I'm going to say 0. So this should be my first point on that curve here. Perfect. What is this? Yeah. Let me just hide this. Oh yeah, this is moved up. I was thinking, what is this? Okay, so I have this starting point and I have the ending points, right? So my starting point is here, ending points are here. If we really want to see the vectors, let's use vector display for that. So V goes to V and A goes to A, and I can see that I'm gonna be moving this curve, not 10 up like it happens right now, but I'll be moving that curve from this point to all these points on my curve. So the vectors seem to be right. When I connect it like this, I have curves. Perfect. Well, the last thing I can do is just loft in the direction of the first curve, right? So here we go. This is the surface, and I can now enable this and really see that it's exactly the same. See, it does this weird thing on, like, it's on top of each other. So like this one and this one, totally the same things. And that means, and this is the reason why I'm showing you this whole thing. This means that every surface should have 2 parameters on itself, right? It should have a t parameter for this direction and another t parameter for the other direction. And that's something we really need to understand, and you know, it's just building on top of this, right? So I'm just gonna take this surface, and for the sake of like everything working nicely, I'm just gonna bake it into Rhino. So right click, bake into any layer. Now we have a proper surface here, and I'm just gonna move it to the side a little bit. And we're gonna reference it so that we can keep this for, you know, having fun with it. Maybe we can move this point a little bit. That would be funny. You know what happens? It's actually sliding with the whole surface. So, you know, some cool features based, well, compared to this. Okay, so I can disable that, and let's focus on our new surface. I'm gonna reference that surface. So again, surface component, right click, set on surface. I just realized I didn't save my file, so if you didn't, I'm just gonna save it right now, because later on I want to show you some data tree related stuff, and it might crash when you do a mistake in there. So yeah, it's gonna be called local coordinates 0.4 from lesson. Okay, here we go, file saved. I kind of hate this when it looks like this, so I'm gonna go to Rhino and type hide command, because, well, you know, it looks awful. So I just had that. Now it's just that surface. I have it here. It's a little bit bent. I like this. And let's do evaluate surface now. So evaluate surface as a component looks a little bit intimidating maybe, but when we provide the surface, it still doesn't work, and there's no T parameter. The thing is that it's now called UV parameters. Maybe you've heard about it from rendering. You know, even meshes have UV parameters for textures and so on. And that's actually a very good reference to understanding this. If you have a mesh and that mesh you know, has some kind of surface and you want to put textures on that, you need to unwrap that mesh into 2D plane and put all the textures into this one rectangle. I hope you've done it already in some other CAD lessons. If you did not, believe me, this is cool. So maybe download Blender and just check out the first tutorial about UV mapping, because it's related to this stuff. But in here we are using, you know, proper mathematical exact T parameters, but it's called UV because it kind of comes from the same mathematical background, I would say. Okay, so this evaluate surface asks for a UV, and if you stop your mouse over the UV input, you're gonna see that it's called UV point. So we can actually use point component, like construct point, for this. And if I provide this, it's working, and you're gonna see a point on the corner here. Then, well, the only thing we need is to put a slider, right, from 0 to 1 like this. And you know, you can rewrite the X for U, and the Y can be rewritten for U and V, and the Z, well, it might be W, but I'm gonna put brackets around it because it doesn't work. It's just on that surface, right? It's not a 3D object. So I'm gonna put this in there, this in there, and now we should be able to move, you know, the sliders and see the plane running on that surface. I'm just gonna make a little adjustment here. Let's say 10. Yeah. So now you can see the plane in there. It should be tangent plane to that surface. That's cool. But what's the problem? Why doesn't it move that much? Yeah, if this is orange, I'm just gonna simulate that. If this is orange like this, of course you need to right click, set one surface, and select the surface we created, or you can use the surface from here. Yeah. But let's get back to this. Okay, so this surface here, well, what's the problem? Why doesn't it run along the whole surface? We provided U and V, it's a point, it's all gray, nothing is orange. Why isn't it running along the whole surface? Try to type the right answer into into the commands, please. So should I make the sliders bigger? Okay, I'll try a bigger slider. I'm gonna say to 1000. So here we go, and wow, where is it? Oh, that's too much maybe. Oh yeah, here we go. You can see that it's running even after the surface is finished. See that? And it seems to be still running on a curved thing. Oh yeah, David, you almost got it. But Barbara is right. It's the magic to reparameterize the thing. So I just wanted to show you, and that's cool, that we can run out of that surface by providing a bigger number than there should be. And again, if we use this domain, but make sure that it's domain squared for a surface, we're gonna see the domain of that surface, and this is gonna be based on that curve we had before. Remember, it was from 0 to 123 or something like that. So yeah, math. You meant math? No, it's magic. It's magic. So even surfaces can be reparameterized. And I'm gonna do that right now. So I'm just gonna disconnect this crazy slider. Um, 0, 0. It seems like, yeah, we're in the beginning of that surface now again. And if I reparameterize this surface, it's from 0 to 1 in both directions. See that? And that's the clever thing with evaluate surface. So in here, if we provide 0.5, we're in the middle of that surface. If we want to be on one edge, just say 0 or 1 at one of these sliders. And this is very useful again, because sometimes, like, how do you get a surface center? Do you want to calculate it from the edges, or like, this is super fast and super smooth. And again, this shouldn't be U and V. This should be T1 and T2. But that sounds stupid. So that's why people started using UV coordinates for that. Okay, and one more stop about like all the outputs we're getting. There's point. There's normal and U and V direction, so 2 vectors, and then a frame, which actually contains all the 4 things over here. So the frame is a plane. Maybe you can use a plane. Sorry, plane. It's a plane. And if you want to construct plane, it usually just asks for point, x direction. So U is the x, and the v direction is the y. So this is the same thing as this one. So we can use the plane right away. And there's this bonus thing. We also know the n direction, like the normal vector of that. Sometimes very useful. What if we wanted to place a box which would be centered on that, like which would be sitting on that surface? Let's do that. So I'm gonna do a domain box this time. I'm gonna use that frame, and well, this is already placed exactly on that surface. So if we want to have, if you want to have boxes on surfaces, this is the way to do it. A question. I'm just gonna keep this, make a copy, and my question is, what if I wanted more than just one box over here? What if I wanted to have, I don't know, 10 times 10 boxes? What should I do? Maybe just make a little bit cleaner here. So yeah, my question is, what, like now I'm having just one plane, that means one box. What should I do to have more than just one box? Anyone? So what if I provide another point with different... Aaron, series is a good tip, but there's a better one than series for this, because we want to keep the numbers between 0 and 1, right? So making a series never exceed 1 actually takes some calculation, and it's too much work anyway. So instead of doing this, because we know this is stupid, right? Having many things connected with shift, we're gonna use range. Again, range, because this domain input, the D, goes from 0 to 1 by default, this is very useful. So I'm gonna just replace these sliders. Let's replace U, and we have some boxes on the U direction, right? So you can see it's still bent like the first curve a little bit. We have some boxes in there. Maybe we can hide the frames now. Just see the boxes. And what if I wanted to have boxes in the other direction? Well, I'm gonna make a copy of this and put it into V, right? Oh, I think we touched on this problem last time. So what should I do to have boxes everywhere on that surface? That's a question. I'm gonna wait for you, try to make it work. In the meantime, I can provide some sliders for this. So I want to have a grid of boxes on my surface, not just a diagonal. What should I do? Yeah, but what should I graft? Graft is the right answer, but which input? Should I graft over here? Or maybe over here? V. Okay, I'm gonna graft V. That's a good answer. Yeah, perfect. So now you can see that data changed. I have a grid, and I'm having a lot of boxes here. We can play with amounts. That's cool. And what if I didn't graft V, and what if I graft U? It works the same. Just the data matrix is flipped. So I can have as many boxes as I want. And they are all aligned with that surface curvature. Pretty neat. Like if you want to do a vineyard rendering, this might be the base, right? Okay, cool. So I'm glad you remember data tree. That's cool. Let me check the file so that I don't forget anything else. Okay, let's continue with the evaluation a little bit. I'm just gonna say a little bit less boxes, maybe like that. And let's focus on one box. So I'm just gonna go here and get rid of the data tree by flattening this. So I go flatten over here, and I'm just gonna select one. So list item. And this is the first one, so I'm gonna provide some slider, and I'm gonna just pick one of the boxes. So here we go. Where's this one? Oh yeah, that's the last one. So I want a box somewhere in the middle. Okay, it goes like this. Okay, this one. This is the box I want. So I have this box. I can click my mouse wheel, and there's this magnifying glass thing. And now I have this zoomed on this little one box. And what I wanted to show you, there's evaluate even for a box. So we should be already familiar with this. So I have this one box. I provide the box, and there's UV, and in this case it's W. That's why I named it like that previously. And these numbers are set to 0.5, 0.5, and 0.5 in this case for all three of them. So if I do 0.5 slider, I can actually have first one, second one, third one. And if all is set to 0.5 by default, this is very useful for selecting middle points of things, because you can put almost anything into a box by using bounding box. So bounding box is a very cool component. You can put anything into a bounding box and then ask for a center. So this is a cool shortcut because evaluate box has all these three input parameters set to 0.5. If I say 0, my the plane moved over here, and you can see that it's aligned with the box. If I say 0 in this case, it moved down here, and if I say 0 in the last one, it's over here at the bottom. Yeah. So again, in boxes, it's already reparameterized. So if you stop your mouse over any one of those three input parameters like U, V, and W, you're gonna see that 0 and 1. Sorry. You're gonna see that 0 and 1 are the numbers which should be on these sliders. Okay, so the funny thing is we can do that for all the boxes, right? If I just bypass this guy over here, I have now planes on every single box, and I can just play with this and this and even that. So evaluate box, I think it's pretty clear. There's one more thing with evaluation, and that's evaluate mesh. So I'm just gonna disable that, move a little bit over here, and I'm gonna first create a mesh by doing populate 3D. I'm just gonna zoom to that. I have this little box of things over here, and then I'm gonna do Delony mesh in the XY plane, so I can hide these points and I have some kind of mesh. Let's keep it like this for now. It's a very rough mesh, but it's a mesh, we can use that because there's mesh evaluate. So evaluate mesh, and this one is kind of tricky because meshes don't have a TV or UV parameter per se. They have something else, and that's called in here it's called parameter. It's a different type of data. So if you right click on the P and if you just stop your mouse over there, you're gonna see that it's called parameter P, and it has different icons. So if I go to my first tab, it should be here somewhere. Let me find that. Maybe it's in primitives. Really? Okay, I cannot see that. Okay, never mind. We're gonna find that parameter by using mesh closest point, because in this case, we're just gonna need to pick a just point, a normal point. Right click, set one point, place it somewhere. I don't care where. We're gonna move with this later, right? Using that. And we're gonna ask that mesh for a closest point. So I'm asking for closest point on that mesh. You can see that it provided me with a point which is exactly here. My point was this one, and this is the place. I'm just gonna zoom into that. 2 points. Okay, so my point is down here, and this is the closest point on that mesh. And what I'm getting is the point. Well, that's the point itself, and then its index. Like face index of the closest point. So this is the face index where exactly the point is. And sorry, I'm kind of tired. And the last thing is the last output is parameter P, and let's look at this guy because it's a little bit different, but again it's the same thing. It looks like this. I'm just gonna make a so that it's one line. And it actually, if we compare this to the index, you're gonna see that the p parameter actually has that index on the beginning. So if I provide this over here, I have that point exactly. So even mesh can have something like a local coordinates on it. And the tricky part with this is that we're using a number of index of the face we're on. So now we're on like one of those two edges here, faces here, and the rest is like 1, 2, 3, and 4 numbers. And that might be kind of tricky, but you can see that this one is 0. So on one of the edge, the distance from that edge is 0. Then there's again a number between 0 and 1, so 0.69 something. That means it's pretty far from, I believe, this point over here. And then there's another number which is saying like 1/3, so that's maybe distance from this point. And well, there's a fourth one, so that's 0 again. That might be the normal direction. So even mesh can have something like a UV coordinates, but you have to know which face is this one. So I'm just gonna quickly try to mesh face, sorry. Is this gonna work like this? No. Okay, yeah. Okay, we have to deconstruct the mesh. So deconstruct mesh. Oh, sorry, I misclicked. Mesh deconstruct. And you know, over here we're gonna have all the faces. So if we ask for the face with index 128, so all the faces, and we're asking for this index. So the output now is this. Remember, this is how mesh works. It's a triangle between a point 23, 16, and 83. So I can just have these numbers into a panel maybe quickly. So 23, 16, and 83. Make sure that you click the multi-line data for this, and we can select those points from here. I might be a little bit too fast now, but I just want to show you that these 3 points are over here. See, 3 points. That means that this face, I can actually make a 4-point surface out of this, or maybe a polyline. That's going to be faster. So I take these 3 points, I make a polyline out of this. I just have to say that the polyline is closed. So toggle. Yes, it's closed. And now we can have boundary surface. So yeah, we can see that it's exactly this this face of that mesh. And you know, these mysterious numbers are actually telling us the position of that point over here. So if I move with this point a little bit to the left, we might see that we flip to a different plane. So I'm just gonna position this properly. Oh no, oh yeah, see, now it jumped. Now we're on index 148, you know, and it's totally different face. So this was just for sorry, yeah, okay. So this was just for explaining that even mesh has this approach, but it might get a little bit more confusing with all the faces in there and indexes of faces. But even on mesh, this works. And now let's see some use cases for this. So I'm gonna just disable that. I think I skipped over one thing in curves, which is quite useful. So let's check that out. Um, Maybe let's go over here where we have evaluate curve. Yeah, I'm just gonna borrow a curve from here, enable that, and zoom to that. So click the mouse wheel. Here I have that curve again. And this curve can also be chopped into little domains. Like remember when we said when we played with the with the division, we used evaluate curve, but there's a brother to this evaluate curve, and that's called subcurve. Because in here the input should be parameter t. Okay, we know that. Maybe just for recap, I just put a range here. This is how it works. It's reparameterized, so perfect. But with the subcurve, the output shouldn't be points like lesser grade geometry, but still curves, because it cuts the curve into smaller curves. Maybe you remember this isotrim. That's the same thing for a curve. So if I provide these numbers, it kind of doesn't work, because this input should be domain. And I'm so glad that this one goes red and it says, well, there's no subcurve, because you just showing me places where it's just a point. So we need to be able to create domains out of these numbers. And let's make it a little bit more playful, because remember we used graph mapper to make it more interesting. So I'm gonna simulate this once more. So I have this graph mapper with a Bezier curve. Wow, this is kind of crazy. Yeah, but I like this. Oh yeah, but you won't have it. That's a plugin maybe. So I'm just gonna have this situation where it goes like this. Yeah, something like that. And I want to cut this curve into like segments. The last one should be the longest, and the first one should be very short. So you can try to do something with components from the intersection tab, but to be honest, like intersections are crazy. Maybe you already discovered, like Boolean operations might fail, or sometimes are unstable or take too much time. So it's so much easier and so much more efficient to work with the UV coordinates of this. So I have the numbers already, but it's just numbers, it's not domains. And I have to do a thing which we already touched on. So I'm just gonna make some space here. This is what we want to do. This is just for remembering. And I have these numbers, so I'm gonna show you the numbers in the panel here. Come on. So some cool numbers. And what I want to do is a domain coming from 0 to 0.003 blah blah blah. So from the index 0 to index 1. And then I want another domain coming from 1 to index 2, right? And then I want another domain coming from 2 to 3, and another domain from 3 to 4, and so on. I hope this rings a bell a little bit, because we've done this with the surfaces on a skyscraper. Again, on our website, there's 2 exercises like it's connected files. You have all the components, and you can test your skills after this lesson is ended, if you totally understand it. Because if you can do this without without you know, referencing your files, it means you totally understood it. So we're gonna do this once over here. So in order to do a domain, we need to, you know, we have this construct domain. We have to have the starting point. I'm going to type it start, and B is for the end of domain, right? For every single domain, we need to have the start, maybe 0, and the end, which is going to be like 0.003919, something like that. And in order to do that, we need to shift the list. Remember? Maybe type if you remember this. I'm gonna show you anyway, but I'm interested. Nobody remembers this, doing shift list to split the data and then put it together in some cool manner. Still no comments, please tell me. Aha, okay, perfect. I'm glad that we're touching this topic again. So if I do a shift list with 1, you know, I'm gonna show you in another panel what happens with the data. You know, see 0 disappeared from the first position, but it got wrapped around the whole list, and it's now on the end. So that's not helpful. So that's why we're gonna say false, that we don't want to. Oh, okay. Barbara remembers. That's cool. So in here, when we say false, now we have a short list, but you know, the first item is totally missing. So this are actually going to be our ends of domains, right? Because the last domain is going to end at number 1, and there is not the 0, because there is none of the domains of the curve should end there, right? So that's what we have now, and we need to make a copy of this and do the same thing, just in the opposite direction. So I'm gonna say -1 in here, and this means when I provide it into the list, we got rid of the number 1 at the end. So that's exactly our starting numbers from the domains, right? Because we start at 0, and we're gonna end at you know, 0.003919. So if I have these two things next to each other, I hope you can see at least a little bit. You know, these are all the starting numbers, and these are all the ending numbers. See, on index 0 we have 0 here, and on index 0 we have 0.003919. So that's exactly what we need. And if we check the domains now, we have nice continuing domains. See? So the first domain ends over here, and the second domain starts at the exact same number. And that's what we wanted. So I can now connect this to my subcurve. And well, the problem is we don't see this properly, but the curve is cut it into segments which resemble the points like this. So in order to see that properly, after all these panels are maybe cleaned up, but I'm gonna keep them, let's do pipe. It's not many, so I can keep the normal pipe. And let's do series for the radius. So you can see that, well, it shouldn't be 0 for the first one, right? Yeah. So let's start at a different number than 0, maybe at 1. And there we go. So this is just for preview purposes, but we can see that every single piece of the curve is actually longer than the previous. It's all based on the same division points, like this guy, right? So this can be useful, and in many cases you really need to do this little trick with shifting lists in order to, generate from just a series or a range of numbers, generate some domains. And then when you have domains, you can cut your surfaces and curves into not points but surfaces and curves again. Okay, let me just try if it works on the other way. Yeah, now these are short and the last one is very long, so exactly what we wanted. And we want to try the other approach. It's very short on the start and also at the end, and there's one big segment in the middle. This maybe if you work in Photoshop or other software doing graphics, you maybe know the famous S curve. So this is the S curve. You can kind of simulate it with using sinus, because it looks like a S curve, but it's not so prominent. You can see that this is very short, this is also very short, but with the Bezier curve you can do even more pronounced S curve like this. And now we have just one huge segment in the middle. It's even better. Okay, so this is maybe something like a continuation of this like curve divisions here. So I'm gonna just place it over here, and the same thing comes for surfaces, and that's actually the homework or the exercise I posted on the website. So that's something you should really check out, how to build a surface which is unequally divided. Let me just quickly, yeah. So this is the case. Sorry, I'm just gonna zoom on that. Okay, here we go. So this surface has some uneven division on it. See that it's very dense over here. Then it goes like in this first direction along this surface. It goes like very dense in the beginning and also very dense at the end. And the same thing happens, but in the opposite way in the other direction, right? So it's not so dense over here. It's very dense in the middle, and then it's not so dense on the other side. So you can check this out. Again, you can see the one is S curve and the other one is well, not so much S curve, right? It's bent like this. I hope it's gonna be reacting, so we can change this. Now we can see that in this direction, yeah, it's kind of fast, but you can see that now it's totally different. See, it's very big step at the end, right? That's because the curve goes fast over here, and it's very dense on this one edge. So yeah, that's something. So this is the file without the coloring, of course. Coloring is a special thing, but it's easy. You can just have a gradient, pick up some numbers, and there are some issues here, but I believe the easiest thing to color a surface like these subsurfaces is to just again use evaluate surface here, and I'm going to show you the planes. Plane. So you can see that the planes, they have a normal vector. So I'm comparing the angle between the normal vector and the z vector of Rhino, and that's why it looks like this. So you can test if you can do that. We can discuss it afterwards if you fail, or just send me the file. Okay, so dividing surfaces. Let me check out the file if we missed some cool thing which is needed. This is not okay. Then this guy. Yeah. Yeah, this is how the file looks. Okay, I guess that's it for today. Any questions? Yeah. Like we still have a few minutes, and I wanted to test the other streaming service, so I think we can use this time to do that. Um, on the website you have a homework file, so check that out. And if you have some trouble trying to solve that, try to explain your problem properly, and I can help you with that. But it should be almost identical to this case, but it's happening in two directions, not just one. So like this is 1D problem, and you have to try to solve it in 2D. Like today's lesson had a lot of hints to solve that, so I hope you're gonna be able to do that. But don't if don't, maybe you need to hear something else. Let me know. I'll help you with that. So questions, really? Okay. Yeah. Okay. I'm saving this file, so this file goes to the website after we finished. And I can see some people connecting on the Teams already, so that's good. Okay. Yeah, cool. Okay, so that means the link is working, that's good. Um, and the thing is, on Teams we can yeah, on Teams we can try talking to each other using the call. So I think after this is finished, I'm gonna try calling, make a group call on the Teams. So if you're connected there, we can try to discuss stuff. Um, as for the last command, Honza, of course, you can have a question about a custom script later, of course. Any questions maybe to the topic we discussed today would be appreciated right now, or we can try to discuss that on the Teams meeting, which is gonna start in like, I don't know, okay, what's the time? Okay, we're gonna start. I'll try to call you on Teams at 11:22. So it's in 3 minutes. Try to click the link, log in to your Teams, and let's continue the discussion in live discussion on Teams. Okay. Yeah, I can see people connecting, so it seems that it works. That's great. Okay, here we go. Here we go. Great. Okay, if there are no comment questions on YouTube now, I think we can finish this, and let's try testing this Teams app. Okay, so bye for now, and see you very soon on the Teams.